It's the fastest object humanity has ever built, lightweight by design. Last year, it reached a staggering speed of over 190 kilometers per second. To put that in perspective, it could circle Earth's equator in about 4 minutes. And yet, even at that blistering pace, it would still take more than 6,000 years to reach the nearest star. That object is NASA's Parker Solar Probe. It will never leave the solar system. Bound to the sun, it accelerates by slingshotting around it, spiraling ever closer until its short mission ends in a fiery collision with Venus. Meanwhile, at just a third of that speed, 2 other machines are quietly making history. Voyager 1 and 2, the first human-made objects to cross into interstellar space. Despite their ancient hardware and broken instruments, they still whisper back to Earth across the void. Each message takes nearly a day to arrive. Most of their systems are shut down to conserve power. But still, they float onward, silent messengers, our first tiny steps beyond the sun's domain. The real question is, will these first interstellar journeys also be our last? It took Voyager 1 nearly 35 years just to exit the heliosphere, the invisible bubble where solar wind meets interstellar gas. It marks, more or less, the edge of our solar system. But if you were there, you wouldn't see anything dramatic, just emptiness stretching for millions of kilometers in every direction. In 30,000 years, Voyager's electronics will fail completely. Its hull will be worn down by endless collisions with space dust. And the famous golden record, our hello to the universe, with a return address pointing back to Earth, will continue to fade in the cold dark. By then, it may pass near another star, not Alpha Centauri, the star we all learned about as kids, but a dim red dwarf called Ross 248. Recent data from the Gaia telescope shows this will likely be Voyager's closest stellar encounter. Even then, it won't get very close. Maybe a couple of light years away, just a cosmic flyby. Even if it had a high-resolution camera, it wouldn't see much. Space isn't just big. It's absurdly, crushingly vast. But what if we did send a new spacecraft to a nearby star system? Right now, a craft no bigger than Voyager, headed to Alpha Centauri or Ross 248. Could we do it in a human lifetime? Say 40 to 50 years? According to recent studies from NASA and leading universities, it would take about 1/3 of the annual energy output of the entire US economy to get it up to speed. That is, if we could somehow harness and unleash that energy instantly, just to launch a single mission. That's how much kinetic energy it would take to get a probe to another star in under 50 years. Which leads to the more uncomfortable question. Is interstellar travel even possible, or are we just chasing fantasies? Is it even worth discussing, when the gap between our dreams and our engineering seems almost hopeless? You might say, anyone can tell you why it won't work, but can someone explain how it might? That's what this video is about. We'll explore answers, real ones, from the people who've devoted their lives to physics, engineering, and space exploration. But first, let's address the question behind every space mission, every rocket launch, every satellite in orbit. Why do we need this? Don't we have enough problems here on Earth? And to that I say, no reason. At least not the kind you're looking for. When humanity took its biggest leaps, launching telescopes, decoding the genome, building artificial intelligence, the right question was never why. The right to ask and to act has always belonged to the minds who dared to look further. From the earliest attempts to explain the heavens to the first satellites hurled into orbit. But I have another more complex answer, and it's not for everyone, so I'll save it for the end of the video. Just a few weeks ago, a remarkable study was quietly published in Nature. It may be the closest thing we've seen yet to a real, purposeful interstellar mission, something that doesn't live in science fiction, but in engineering labs. Some of you might remember the idea behind Breakthrough Starshot, a project to launch ultralight space sailcraft. The concept is bold. Deploy a spacecraft no larger than a microchip, attached to a reflective sail about the size of a parking space, 10 square meters. In the vacuum of space, the sail unfolds and a powerful ground-based laser beam pushes it forward. The entire payload weighs just 2 grams, 1 gram for the sail, 1 for the electronics. In theory, this setup could accelerate to 1/5 the speed of light, meaning the probe could reach Alpha Centauri in about 20 years. But the challenge is massive. These sails must be absurdly strong to survive extreme acceleration, going from 0 to 60,000 kilometers per second in under half an hour. At the same time, they must dissipate enormous heat from the laser without melting and reflect that same laser light as efficiently as possible, across a range of wavelengths distorted by the Doppler effect as the probe speeds up. And all of that with a total mass under 1 gram. Impossible. Nearly. So far, attempts to make such sails involved electron beam lithography, the same slow, expensive technique used to make advanced semiconductors and some quantum computer components. This process involves painstakingly burning billions of nanoscopic holes into the sail, one at a time. It takes months and millions of euros to produce just a single sail. But the new study proposes an entirely different approach, one that could be 9,000 times cheaper and dramatically faster. Instead of etching holes individually, the researchers created a pentagonal nanostructure that can be printed all at once using the same lithographic techniques already employed in chip manufacturing. This brings the cost of a single sail down to just 3,000 euros and cuts the production time to a couple of days. If this method proves scalable and works outside of the lab, we may soon be able to produce thousands of these sailcraft, cheaply, rapidly, and at scale. But why? What can you even do with a 2-gram spacecraft? Surprisingly, quite a lot. A single microchip can already house sensors, a communication system, and even a tiny camera. All of that is technically feasible today. Power, however, remains the bigger hurdle. How do you supply reliable energy in deep space, in the cold and the dark, using less than 1 gram of material? Radioisotope batteries, like those used in medical implants, are a possible solution, but not an easy one. Yet even energy is not the biggest problem. The real killer is survival. Once these tiny spacecraft exit the heliosphere, they'll be exposed to raw interstellar space, where the sun's protective magnetic field fades and space becomes significantly harsher. Even microscopic particles of dust, traveling at 20% the speed of light, can tear these nanometer-thick sails apart. Even molecular collisions at such speeds cause damage. And over 20 years of travel, the erosion adds up. This means we'll need to send not just one, but many, a fleet, a swarm of sailcraft. Only then can we be confident that a handful will survive the journey. But again, why do it at all? The fact is that we know very little about what specifically awaits us when we cross the conditional boundary of the heliosphere and find ourselves in interstellar space. The density of dust, the intensity of radiation, the real composition of interstellar gas. We cannot model it accurately. We cannot simulate it properly. Even our best probes, Voyager 1 and 2, weren't built for this. Their instruments were designed for flybys of planets and moons, not for studying the void between stars. And even if their systems were still running at full capacity, they wouldn't tell us much about what they're actually encountering out there. Launching a new generation of sailcraft is our only chance to learn, not from guesses or computer models, but from direct experience. Just like new aircraft must fly thousands of hours before engineers fully understand their limits, space probes must traverse interstellar space before we know how to survive it. Dust, gas. What else is there to study out there, really? Well, everything, even the starry sky itself, and how to navigate through it. Because while we've gotten used to flying spacecraft around Earth, we tend to think we've mastered spaceflight and space navigation. Space probes seem to reach their destinations. We always know where they are, so what's the problem? The problem is this: our navigation systems are fundamentally limited to our own solar neighborhood. They were designed for spacecraft moving at a crawl compared to light just tiny fractions of a percent. At those speeds, relativistic effects are negligible, and accelerometers, Earth-based radars, and telescopic tracking are enough. But once you're moving at a significant fraction of the speed of light, or traveling for decades into deep space, these systems begin to break down. Navigation becomes unreliable. Signal lag stretches from minutes to hours to days and eventually weeks. Small errors in trajectory become massive deviations when you're billions of kilometers away. If we were to send a spacecraft on a 50-year journey to Alpha Centauri, and we relied only on current star charts uploaded at launch, by the time it arrived, the map would be outdated. The stars would have moved, the orientation would be off, tiny miscalculations would become astronomical detours. To give you a sense of scale, right now, with all our telescopes and simulations, we can't even say for sure whether the Milky Way and Andromeda galaxies will collide. We think they will, in about 4.5 billion years, but even that is based on models with margins of error. So how can we trust our navigation over light years? We'll need to develop entirely new methods of deep space navigation. Star mapping in real time, autonomous celestial triangulation, onboard recalibration. And for that, we need scouts. That's where these tiny, lightweight laser sailcraft come in. They may seem modest, but in truth, they are our first eyes beyond the cradle. They can send back data on what interstellar space is really like and help future missions find their way. We're not talking about crewed ships yet. Let the robots go first, and not just any robots. Intelligent, self-learning explorers. Eventually, these systems could be hybrid, combining electronics with biological elements, gaining both adaptability and resilience. We haven't even begun seriously designing robotic systems built specifically for interstellar missions. But we will. That's another conversation, and a necessary one. Because the truth is, to send even small autonomous explorers, we'll need to solve a much bigger problem: propulsion. Let's talk about what kind of engines could actually take us to the stars, not in thousands of years, but in decades. This isn't science fiction. These are concepts and prototypes that scientists and engineers are working on today. Ideas rooted in real physics. But first, a little history. If you or someone you know ever gets deeply interested in interstellar travel, you'll eventually encounter a very old, very stubborn formula. It's the foundation of all rocketry, derived in 1903 by Konstantin Tsiolkovsky. The Earth is the cradle of humanity, but one cannot remain in the cradle forever. A romantic, an engineer, a mathematician, Tsiolkovsky saw farther than anyone else of his time. Airplanes had barely taken off, but he was already calculating trajectories to the stars. His famous equation describes how a rocket accelerates by expelling mass, fuel, at high speed in the opposite direction. The higher the exhaust velocity, the faster the spacecraft can go, and the less fuel it needs. The critical term in this calculation is specific impulse, a measure of how efficiently a rocket uses its fuel, usually expressed in seconds. Simply put, the higher the specific impulse, the better. Now here's the problem. All current rockets use chemical propulsion, usually some combination of liquid hydrogen and liquid oxygen. The maximum specific impulse, around 450-500 seconds in ideal lab condition. In reality, it's often less. To reach Alpha Centauri in under 50 years, a spacecraft would need to reach about 10% of the speed of light. Even the most advanced chemical rockets wouldn't get us there in 13,000 years. Yes, 13,000 years. That's what the math says. These aren't my numbers. They come from the same physicists and engineers whose work I studied for this video. Even if we move to exotic fuels, nuclear helium, or even metallic propellants currently being researched, the outcome doesn't change dramatically. You'd still need an astronomical amount of fuel to achieve escape velocities sufficient for a human lifetime interstellar mission. So where does that leave us? Exactly where Tsiolkovsky pointed over a century ago. We need a different kind of engine. Not one bound by chemical explosions, but something radically more efficient. Let's not forget another way to gain acceleration in space: gravitational slingshots. They work alongside any propulsion system, except the fantastical ones like warp drives, which would require discovering new laws of physics and reshaping space-time itself. Gravitational maneuvers are brilliant because they let us alter a spacecraft's trajectory and speed without burning fuel. When a probe nears a planet or massive body, it accelerates as it's pulled into the gravity well, then slows again as it escapes. But here's the trick. If the spacecraft enters the planet's gravity while moving in the same direction as the planet orbits the Sun, then exits in the opposite direction, it can steal a bit of that orbital momentum. This is how Voyager, and especially Parker, gained far more speed than they had at launch, without using extra fuel. Now add engine thrust at the closest point of approach during a maneuver like this, and you've got an active gravitational assist, which can dramatically boost a craft's kinetic energy. A few years ago, scientists ran a fascinating simulation. Instead of planets, they used a pair of neutron stars. The result? A passive slingshot could push a craft to 1% the speed of light, but if you added a thrust burn during the closest approach, 27% the speed of light, 81,000 kilometers per second, that's fast enough to reach Alpha Centauri in just 15 years. Theoretically, black holes could do the same, but we don't have any nearby to try that with. Now, nuclear engines. These are currently the most promising option when it comes to real-world tech. 1 kilogram of uranium-235 releases 6 million times more energy than the same mass of chemical rocket fuel. That's game-changing, if we can harness it. The simplest nuclear engine design? A nuclear thermal rocket. You use radioactive decay to heat up a lightweight propellant, like hydrogen, which then blasts out through a nozzle. Both the US, Projects Rover and Nerva, and the Soviet Union, Project RD-410, built test systems like this in the 70s and 80s. They worked. The only real limit? The reactor materials. Metals like tungsten and molybdenum can withstand up to 3,000 kelvins, high enough to seriously heat the propellant and achieve faster exhaust speeds. These rockets can hit a specific impulse, a measure of efficiency, of about 850 seconds, compared to 450-500 for chemical rockets. Some estimates suggest that modern materials could push that up past 900. But we can do better. By using liquid nuclear fuel, we could squeeze even more heat out of every gram and double the efficiency. This isn't science fiction. Liquid-fueled reactors were tested for power plants in the mid-20th century. There's nothing stopping us from adapting the concept for deep space travel. Next, plasma reactors, where uranium is turned into a plasma under high pressure. These systems could reach temperatures of 100,000 kelvins and theoretical impulses of 7,000 seconds. Still, that would only cut the trip to Alpha Centauri down to about 8,000 years. Not great. So let's go bigger. Impulse nuclear engines, also known as Project Orion. These would detonate atomic bombs behind a spacecraft, using each blast to push it forward. This was a real Cold War-era concept, shelved due to the obvious risks, but theoretically, a ship carrying hundreds of thousands of bombs, weighing around 400,000 tons, could accelerate to 3% the speed of light in just 10 days. Alpha Centauri in 130 years. I'll stop here, because beyond this, we enter the realm of antimatter engines, fusion drives, and other near-mythical technologies. They're not impossible, they just don't exist yet. That deserves its own video, engines that shouldn't exist but might. In the meantime, I'll answer the question from the beginning of the video. Why should we venture into this cosmic abyss when there is so much to do here at home? I promised a simple yet complex answer. It is important to me, but not to everyone. However, not everyone who started watching is still here. That is, only those who may find it truly interesting, and perhaps even useful. When Nietzsche said God is dead in The Gay Science, it wasn't a prophecy, it was an obituary. The Industrial Revolution had stripped Western society of its old values, the divine order, the sacred text, and replaced them with steel, smoke, and scientific progress. For the first time, humankind saw itself not beneath God, but beside Him, maybe even above Him. We weren't kings anymore. We were creators, rulers of nature, shapers of destiny. And in our rise, we tore each other apart in 2 world wars and created weapons that could end civilization in hours. In killing God, we crowned ourselves. But the new king wasn't ready. Humanity could reshape the world, but it still couldn't master itself. And so, once again, people began searching. Not everyone found God in religion. Many found Him in power, in wealth, in distraction, or in nothing at all. But for some, that absence felt like an abyss, a spiritual vacuum that no salary or vacation or dopamine hit could fill. And that's why we need space, not just to explore, to become something greater than ourselves. For those who won't find God in a pulpit or in consumerism or in ancient texts, space is the new sacred. It is the void, the Alpha and Omega, a God who doesn't speak, doesn't care, and won't save us, but who still might make us worthy of saving ourselves. Tsiolkovsky said, "Earth is the cradle of humanity, but one cannot live in the cradle forever." He never saw a human leave that cradle, but we did, and now we must keep going. Because space doesn't just expand our boundaries, it reshapes our priorities. It reminds us of scale, of wonder, of the difference between what's urgent and what's important. And that's why we go. See you in the comments.